Good morning, professors. Sorry. We are from the Hong Kong Chinese Women's Club College. Our team registration number is 161061. I'm Ivan. It's our honor to be here presenting on the fruits of our research on family of triangles, from medians to concurrent line triangles and angle bisectors triangles. A simple idea sparked off the whole research. Given an arbitrary triangle, can we form a new triangle with the three medians of the original triangle? Now, using vector and matrix operations, we formulated the relationships between the sides of the angles and the medians of the triangle. This gives us theorems 1 and 2 on pages 6 and 7 of the report, respectively. Coincidentally, by using cosine formula to find the included angles between the medians in the original triangle, we discovered that the medians satisfy the cosine formula, and thus the three medians must form a valid triangles. This what we call a median triangle now, with the three angles equal to the corresponding included angles of the medians in the original triangle, giving us theorem 3 on page 8 and of the report. This is an elegant alternative proof for this theorem. Refer to figure 5 on page 9, which is also here, the figure. We extend BMB by 1/3 to E. Then central G divides each median in the ratio of 2 to 1. Thus, G bisects BE and MA bisects BC, which is right here. And by midpoint theorem, CE is equal to 2 MAG and equal to 2/3 of MA. And MAG is parallel to CE. The length of the three sides of triangle GCE are 2/3 MA, 2/3 MB, and 2/3 MC. This illustrates that a triangle with the length of the three sides being MA, MB, and MC can be constructed, and MAG is parallel to CE. Thus, the triangle has alpha, beta, and gamma as its internal angles. A similar technique is used to prove some other theorems in this report. Armed with this knowledge, we defined a family of triangles in which every triangle is formed from the medians of the previous triangle. We then went on to explore the properties of such a family, and we Theorem 4 on page 11 of the report stated that the n+2 triangle of the member of the family of median triangle is similar to the nth member of the median triangle family, with the corresponding side ratios being 3 to 4. This is one of our most notable results. We then went on to find the relationships of the sides, areas, and angles among the members of the family. And here is a list of all some of the theorems for the median angle triangle family, and we can see that a lot of them are related to our magic number 3/4, and echoes with theorem 4. However, the one point worth noting is that the correlation between members is not only bound by its similarity between alternate members. For instance, in theorem 7 on page 14 of the report, the ratio of the area of the n+1 triangle member of the family has an area with the ratio of 3 to 4 with the nth member of the family. And the sum of cosecant square of all angles is remain constant for all members. This shows that despite not being similar, successive triangles still have a constant area ratio and other correlation. Now that we have dealt with basically most aspects of the median triangles, we went one step further to generalize the situation. Once again, suppose we are given an arbitrary triangle. We construct three civilians dividing the corresponding opposite sides in arbitrary ratio, say P to 1 in BC and 1 to Q in AC. Then we wonder if we can form a new triangle, a so-called concurrent line triangle, from the three civilians. By doing vector and matrix operation again, we found the relationship of the civilians and the sides as shown in Theorem 17 and 18 on pages 26 and 27 of the report. However, we hope to mimic the scenario in the median triangles case, that the included angle between the between the civilians corresponds to the included angles in the new triangles. And we discovered that P plus 1 LA, Q plus 1 LB, and P plus Q LC did satisfy such condition and could form a new triangle. This gives us Theorem 19 on page 28 of the report, and on page 33 of the report, we define the three sides of the concurrent triangle as P plus 1 over P plus Q LA, Q plus 1 over P plus Q LB, and LC. With this new definition, we proceeded to explore the properties of the family of concurrent line triangles. Theorems 20 and 21 on pages 34 and 36 of the report basically mirrors theorems 4 and 7 of the median triangle case, telling us that the areas of successive members of the family and the corresponding sides of the alternate members of the family have a ratio of P plus Q plus PQ to P plus Q whole squared. Here are the sets of the equation for the concurrent line triangles family, and we can see that and we can see that there are once again we can see the ratio of P plus Q to P plus Q whole squared in a lot of these theorems, and once again relating different triangles by this ratio, indicating that as long as we know P, Q, and two successive members of the family, we can effectively solve for any quantities of the triangles of the family by multiplying them to a power of the ratio P plus Q plus PQ to P plus Q whole square. So this is our magic number once again, and if we put P and Q equals to 1, it will reduce to the median triangle case. We finally comes to one last special case, the angle bisector triangle family. We explore the family of triangle formed from the angle bisectors using the results of our research. However, it was proven difficult as the angle bisector cut the opposite sides in varying ratios for different members of the family. We only managed to derive the Theorem 26 and Appendix 4, in which PQ only stay consistent for all members of the angle bisector triangle family, if and only if the triangles are equilateral triangles. These are the major findings of our reports, and several months ago, and now here we are with a new way to explore and connect different triangles, the fundamental of geometry. In the future, if given the opportunity, we would like to deepen our research in areas such as the properties between the angle bisector triangles and other concurrent line triangles family with different conditions for the concurrent point. Thank you for your time.
Okay, thank you.
Thank you.